Hi everyone. This video begins a series of 3 videos talking about inverse trig functions. This one is about inverse functions. I want to go back over some things that will be very, very helpful. These are concepts that we went over in pre-calculus, in trig mostly, and they will be very, very helpful as we begin to take the derivative and the integral of inverse trig functions. Some of you, when you hear review, start fast forwarding. Please don't do that. Every single one of you needs to go over these concepts. Okay, so the first thing we want to do is we want to look at inverse trig functions from a graphical point of view. And so you can see here that I have both the sine and the cosine functions. This one actually has sine on it, but I have the sine and the cosine functions graphed. And you can see on the sine function, remember that a period is 2 pi. The amplitude is 1 and -1, so it bounces between the two, and this is halfway between. Amplitude is really just from halfway between and up. Okay, remember that sine goes through the point 0, 0, but cosine does not. And that's because these are angles along the x-axis. Right? These are angles on the unit circle. They're just stretched out long like this. You can see that the cosine has a period also between 0 and 2 pi. The other thing about cosine and sine functions is that they are translations of each other. In other words, you could move them right and left and they would sit on top of each other. Notice that the scale is different on these. So they look like they're different, but they're not. Same scale. Same period, same amplitude, different scale along the x-axis. All right, so once again, we know that the definition graphically of an inverse is that it passes the horizontal line test. In other words, if there is one single y value for every x, well, if you do this, you can see that if I draw a horizontal line through either of these, it fails numerous times throughout infinity. So in order for this graph to have an inverse, we have to restrict the domain. And we restrict the domain of sine differently than we do cosine. Because if you look here, this is negative pi over 2, this is pi over 2, right? You can see that this little red snippet passes the horizontal line test. But if you do the same thing from here to here, negative pi over 2 to pi over 2 for the cosine graph, it does not. So here, from negative pi over 2 to pi over 2, this area right here on the unit circle would be first quadrant. This is the first quadrant. And this from negative pi over 2 here would be the fourth quadrant this way. Okay? So, but if we do the same thing here, right, we don't get that. So for cosine, this is cosine, and any inverse of cosine, to have an inverse, I'm going to have to move and restrict the domain between 0 and pi. Well, on a unit circle, that's going to change the quadrants from first and second. So not fourth, because first and fourth cosine is positive. So we need one where it is positive, and we need a quadrant where it is negative. And so here for cosine and secant, positive and negative. Now, if you didn't pick that up in trig, this is really important for you to know. This is why we have to restrict the domain of these two functions. Okay, evaluating the inverse of a function. There are a couple of things here that are really important to remember. And the first is this, that when you're evaluating a sine function, you are taking the sine of an angle, and the sine of an angle is going to equal a ratio. And you remember from ancient trig that sine is opposite over hypotenuse, so ka to a, yes? All right, so if you're taking the inverse, right, you switch the two. And so you would take the arcsine of a ratio is going to equal an angle. And the restricted domains that you are using have to do with what we said on the other side, which was, on the other slide, which was that in order for it to be an inverse, you have to restrict the domain so that it passes the horizontal line test. So we know that odd functions like sine, tangent, and then their reciprocal functions, cotangent and cosecant, all have the same domain, right? So it'll be the negative pi over 2 to pi over 2. And then the cosine, the even functions, the cosine function and secant function are restricted from 0 to pi, or first and second quadrants. Okay, but also remember too that whenever you are taking the inverse function, like say for instance you said that the cosine of what is 1/2, remember that this is not an inverse. So it could actually be many, many, many angles. So that theta, right, would be pi over 3 plus all the angles that are coterminal to pi over 3, plus or minus. And remember that the period of a cosine function is 2 pi, so it would be 2 pi times n. So when you write it like this, you're trying to find all the angles for all time, but you are not finding the inverse. You're just finding all the angles theta that would make that true. When you're finding the inverse by evaluating these functions down here, you are using the restricted domains that we talked about. So it won't be all of them, it will just be one angle. And if the ratio is negative, it will be in the negative quadrant. If they are positive, they will be in quadrant 1 every time. Quadrant 1 if it's positive. However, if it's on a quadrantal angle, it will be on the axis between the restricted domain. So this is really important that you understand this, because this was really hard in trig, I think, for students to realize that you have to restrict the domain or it's not a function. Okay, so the arcsine of, you are looking for angles. So the arcsine of this angle is going to be negative. It's sine, so it's odd. So it's also going to be negative, fourth quadrant. It'll be negative pi over 6. The arc cosine of 0 is a quadrantal angle. And if you think about where that is, cosine is 0 here and here. But only here is in the inverse domain. So this angle would be pi over 2. For arctangent, this is positive. No brainer, first quadrant. Don't even have to think about it. 1, 3, pi over 3. This one, on the other hand, is not on the unit circle. So I would have to use a calculator, which I just happen to have nearby, which is the, so I would hit arc, I would hit second sine of 0.3 and get 0.304692 5. And there we go. Okay, so the next thing we want to do is solve an equation, right? And we know that because these two functions, the arctangent and tangent, are inverses of each other, they undo each other in an equation. So what we're after is we're trying to solve for x. And so we need to find out what x equals. And so to undo the arctangent, I'm going to tangent both sides. So the tangent of the arctangent, and I have to do both sides, right? So these are inverses of each other, and I'm going to end up with 2x minus 3 equals the tangent of pi over 4. Pi over 4, remember, sine and cosine are the same value, so this is 1. So 2x equals 4, and x equals 2. That's it. That's all there is to it. So you're just going to undo both sides. Okay, so another method to evaluate an inverse function, or a function that looks like this example, is to use a right triangle. But let's remember that since we're taking cosine of something in parentheses, we're taking cosine of an angle. Cosine of an angle is going to equal a ratio. So our answer to this problem is going to be a ratio. Okay, So the first thing that we want to do is we want to use this arcsine of x to put in values onto a right triangle, right? So we know that this is an angle, and so the arcsine would be the ratio of x over 1, opposite over hypotenuse. And we know from the Pythagorean theorem that the hypotenuse squared minus the leg squared is equal to the other leg. So we now have all three measures, or not actually a measure, all three expressions for each of the three sides of this right triangle, hypotenuse and the two legs. Okay, so then once we've done that, we use the angle to draw the triangle. Then we're going to take the cosine of that angle, theta, and that will be my ratio. Well, the cosine is going to be the side adjacent, 1 minus x squared, over the hypotenuse. So this would be the answer, and this is my ratio. This is just over 1. Okay, so continuing to use right triangles to evaluate, I have y equals arcsecant of the square root of 5 over 2, and I want to find the ratio for tangent of y. All right, so once again, keeping in mind what we have here, this is a ratio, right, because it's arcsecant. This is an angle, and I'm trying to find the tangent of an angle. Okay, so I'm going to use the ratio in my triangle, and this is going to be my angle y. All right, so I know that the secant of an angle is equal to 1 over cosine of an angle, and that is equal to a ratio, which is square root of 5 over 2. Well, okay, if secant is equal to 1 over cosine, then cosine is going to be equal to 1 over secant, and so that's going to be equal to the ratio of 2 over the square root of 5. Well, I know cosine, even if I don't know secant, so that's going to be adjacent over hypotenuse. The other way you can check to see if you got it right is if it's backwards, square root of 5 is bigger than 2. 2 is the square root of 4, right? So if you get them backwards, the hypotenuse has to be the longest side. Okay, so then I want this third side over here because I need tangent. And the tangent is opposite over adjacent. So I'm going to have the hypotenuse squared minus the leg squared, right? So that's going to be 5 minus 4, which is 1. So if I'm going to find the tangent of y, that's going to be opposite over adjacent, which is 1/2. And that's it. So in class, what we're going to do is a lot of these review problems to kind of remind you how to use a right triangle and kind of bring all of that trig back to the forefront before we launch into derivatives and integrals. All right, so I'll see you in class.